Okay, in this video, we're going to talk about polarity of bonds and then apply that to figuring out if a molecule overall is polar or nonpolar. Before we can talk about polarity of bonds, though, first I need to remind you about electronegativity. So remember that electronegativity is like when an atom is bonded to another atom, it's its ability to pull electrons towards itself. So it's like, if you have a covalent bond, it's kind of like you and, imagine that you're an atom, you and another atom are sharing a blanket. Whoever is more electronegative is going to pull the blanket more towards them, right? You're still like sharing the blanket, but one person gets more of it. So when we have atoms that have pretty much the same electronegativities, then we call that type of covalent bond non-polar. And I think it's like my pulling blanket analogy. It's useful because it's, if you have similar electronegativities, it's a non-polar. There's nobody pulling the blanket. So it's non-polar when two atoms of the same or similar electronegativity, which I'm just going to abbreviate as E-neg, electronegativity are bonded. Actually, I could write that out. So again, electronegativity is like how good something is at pulling electrons towards itself when it's involved in a bond. Okay, so examples of bonds that we see in organic chemistry all the time that are nonpolar are when we have anything that's bonded to another atom that's exactly the same as itself. So like a carbon-carbon bond, or maybe an oxygen-oxygen bond, or like a fluorine-fluorine bond. Those are all classified as non-polar bonds. The ones that we see the most common, however, are carbon-carbon bonds and carbon-hydrogen bonds. Now with the carbon-carbon bond, it doesn't matter if it's a carbon-carbon single bond or if it's a carbon-carbon double bond or even if it's a carbon-carbon triple bond. Since carbons have, like both of these carbon atoms have exactly the same electronegativity, they're sharing the blanket perfectly. So carbon-carbon, carbon-hydrogen, and in fact any atom with itself. So any atom with another one that's the same type of atom, so like an oxygen-oxygen or fluorine-fluorine, those are all classified as non-polar bonds. A covalent bond, on the other hand, is classified as polar. So polar when we have atoms that have different electronegativities. So different electronegativities. Now, if we have that the electronegativities are different enough, if they're like an extreme difference of electronegativities, then we classify that as an ionic bond, where like the electrons are not shared anymore. There's one atom who's totally stealing the electrons from the other in the bond. But that's not what we're talking about right now. We're talking just about covalent bonds. So we have polar and we have nonpolar. So the common examples that we see of nonpolar bonds in organic chemistry are, honestly, it's pretty much everything except for a carbon-carbon or a carbon-hydrogen bond, or any atom that's bonded with itself. The common ones that we see are carbon-oxygen, carbon-nitrogen, carbon-halogen, that's what the X is representing, so halogen, and then hydrogen-oxygen, hydrogen-nitrogen, and hydrogen-halogen. So remember how in your 121 class you probably had to go through and you had an electronegativity chart and you had to subtract one number from the other and then figure out what range it was in? For organic chemistry, we really don't need to do that because these are, by and large, the types of bonds that we see. And so as long as we can remember, okay, carbon-carbon, carbon-hydrogen, and any atom with itself, as long as we remember that those are all nonpolar and everything else is polar, then we don't have to go back to that chart of electronegativities and do the subtracting thing and comparing it to our chart. So to write that out, again, if carbon is bonded to anything, and by write it out, I mean it's already written out here. If carbon is bonded to anything that's not carbon or hydrogen, the bond is probably polar. So, for example, let's apply this to a molecule where we are first identifying all of the polar bonds, and all of the nonpolar bonds too. Okay, so here I have drawn the Lewis structure of methanol. And so what I'm going to do is I'm going to classify each of these bonds as polar or nonpolar. Okay, so this one, well, carbon-hydrogen, 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 those are all nonpolar. Carbon-oxygen, though, that's a polar bond, and an oxygen-hydrogen, that's also a polar bond. Now that we've identified that we have two polar bonds in here, there are a couple of different ways that we can represent it. So I'm going to show you both of those ways of representing the polar bond. Now, the first way is with an arrow that looks like this. So we have an arrow that has like a little tail on the end. And in this arrow, we call this a bond dipole. The arrow is pointing toward the more electronegative element. So Ellie, you ask, how do you tell which element is more electronegative? Well, you look on the periodic table and you remember that fluorine is the most electronegative element. And as stuff gets closer and closer to fluorine, it's more and more electronegative. So if you look at where carbon is on the periodic table versus where oxygen is on the periodic table, you can see that oxygen is much closer to fluorine. Then there's nitrogen in here too. So the oxygen is more electronegative than the carbon, and being more electronegative, it means that in this bond between the carbon and the oxygen, it's going to pull the electrons more towards itself. Okay, so same thing with the oxygen and the hydrogen. The oxygen is more electronegative, so it's going to pull the electrons towards itself. Okay, so we can represent this this bond polarity as bond dipoles. We can also show this with partial charges. So when we know that electrons are negatively charged, so when we have electrons that are pulled more to one side, wherever they're pulled towards is going to have a higher negative charge, right? You add more negative and it's going to be more negative. So where the electrons are being pulled towards, so that's the electronegative element, that is going to have a partial negative charge. Well, what happens to the elements that have electrons more pulled away from them? Well, if you're minusing a negative, so you're pushing away, or you're getting rid of some of that negative charge, what that leaves is a partial positive charge. So, in summary, these bonds that we just labeled are polar. So these bonds, the carbon-oxygen and the oxygen-hydrogen, these bonds are polar, and we represent them. So they're represented with partial charges. So that's these funky little things. So partial charges, that's the partial plus, partial minus, or a bond dipole arrow. So the arrow looks like this, and in the arrow is pointing to the more electronegative element. So again, different ways of representing polar bonds. What we're mostly interested in, though, is not individual polar bonds, but applying those polar bonds to a whole molecule to figure out if that whole molecule is polar or nonpolar. So I'm going to give you a quick definition for a polar or nonpolar molecule, and that is this. A polar molecule is one that has an overall uneven distribution of electrons. So in other words, there's lots of separation of charge. Okay, so I just paused the video and wrote that out. A polar molecule, there's an overall uneven distribution of electrons. So there's lots of separation of charge. A nonpolar molecule, on the other hand, nonpolar molecule, and I'll write this out while I'm recording, this has an overall even distribution of electrons. So even distribution of electrons. So there is little to no separation of charge. So little to no separation of charge. So those are our definitions. The key word that I want you to pay attention to here is even and uneven. So for a polar molecule, we're looking for uneven distribution of electrons, and for a nonpolar molecule, we're looking for an even distribution of electrons. So next, this is where we're going to put these two concepts together, the polarity of bonds and the shape overall of molecules. So we're going to go first through the general chemistry way. So that's meaning like probably through the way that you learned or similar to the way that you learned in your 121 class. I'm not going to go through the organic chemistry way quite yet. We're going to wait for that until we cover like new content, since right now this is all review. But just know that that's coming, that there is another way for us to figure out if a molecule overall is polar or nonpolar. All right, so the general chemistry way is we examine the molecule and see if there are only nonpolar bonds. If there are only nonpolar bonds in the molecule, then overall the molecule will be nonpolar. So overall nonpolar. And this is really nice because it works with both small molecules and big molecules. So say that we have CH4. In this, we can see, okay, there are carbon-hydrogen bonds, and those bonds are all nonpolar. Therefore, this molecule is definitely going to be nonpolar. There's nobody hogging the electrons anywhere. Okay, let's look at another example. Let's look at something a little bit bigger. Let's look at something that has a bunch of carbons and a bunch of hydrogens. Bear with me for a moment. Okay, this molecule, it's bigger than the methane molecule, so than this one up here, but it is still nonpolar. And we can tell that it's nonpolar because it only has nonpolar bonds. So again, if there are only nonpolar bonds in the molecule, overall, it's nonpolar. Next up, if first off, for this, the molecule has to be small. So if molecule small, and there's one and only one bond that's polar, then overall our molecule will be polar. And so when I say, like, if the molecule is small, usually what that means is that there's only one central atom, or maybe two central atoms. Okay, so an example of this might look like this. So we have CH3, then F. Okay. So looking at this, the carbon-hydrogen bonds, those are all nonpolar, but the carbon-fluorine bond, that is definitely like very, very polar, because fluorine is super electronegative. So the bond dipole will look like that. We'll have a partial negative charge on the fluorine, partial positive charge on the carbon, and so overall we do have a separation of charge. So this molecule would be classified as polar. Okay, let's do one other one. So we have HC triple bond N. All right, so the carbon-hydrogen bond, that's nonpolar. The carbon-nitrogen bond, though, that is polar, and the bond dipole is pointing, the arrow is pointing towards the nitrogen. There's a partial negative charge on the nitrogen and a partial positive charge on the carbon. So with both of these cases, if we have either only nonpolar bonds, or if the molecule is small and there's one and only one bond that's polar, the shape doesn't really matter, right? Like, we didn't, in order to figure this out, we didn't have to go through first saying, oh, this is linear, or oh, this is tetrahedral, or whatever. We could just count the number of polar bonds and say, bam, there you go. What happens, though, if there is more than one polar bond? That's what we're going to get to next, and that's where it gets a little bit more complicated, but also more interesting. I'll see you then.